Understanding Sklearn Gaussian process kernels and hyperparameters. Gaussian processes GPs are powerful tools for regression and classification tasks. They provide a probabilistic framework to model the underlying function generating the data. A key component of GPs is the kernel function, which defines the similarity between data points. Sklearn provides a rich set of kernel functions, each with unique properties and hyperparameters. The role of hyperparameters. Hyperparameters in kernel functions control the shape and characteristics of the resulting GP model. They are crucial for achieving optimal performance on the given dataset. Finding the right hyperparameter values is often a challenging task, requiring careful exploration and analysis. Available kernels in Sklearn. Sklearn offers a range of built-in kernels, each with its own strengths and weaknesses. Here's a breakdown of some prominent ones. 1. RBF kernel radial basis function. Formula kx1, x2, xp, x1, x22 to length scale 2. Hyperparameter. Length scale controls the smoothness and how quickly the kernel decays with distance. Larger values indicate smoother functions, while smaller values lead to more local behavior. Key features. Most commonly used kernel provides a smooth and continuous function. Captures smooth, nonlinear relationships. Can be computationally expensive. When to use for data exhibiting smooth, nonlinear dependencies. 2. Linear kernel. Formula kx1, x2 by 1 by 2. Hyperparameter none. Key features. Simplest kernel. Assumes a linear relationship between data points. Leads to a linear model. When to use when the data is linearly separable or for quick exploration. 3. Polynomial kernel. Formula kx1, x2 gamma x1 by 2 coa 0 degree. Hyperparameters. Gamma controls the scaling of the dot product. Coa 0 constant term. Affects the behavior near the origin. Degree controls the degree of the polynomial function. Key features. Captures nonlinear relationships through polynomial functions. More flexible than linear kernel but may overfit easily. When to use when there are polynomial relationships in the data. 4. Laplacian kernel. Formula kx1, x2 xp x1 x2 length scale. Hyperparameter. Length scale controls the smoothness and how quickly the kernel decays with distance. Key features. Less smooth than RBF kernel. Captures sharper transitions. When to use for data with sharp edges or discontinuities. 5. Rational quadratic kernel. Formula kx1, x2 1 by 1 x22 2 length scale 2 alpha alpha. Hyperparameters. Length scale controls the smoothness and how quickly the kernel decays with distance. Alpha controls the shape of the kernel. Larger values lead to smoother functions. Key features. Combination of RBF and linear kernels. Provides flexibility and allows for smoother transitions. When to use for data with both smooth and sharp features. 6. Matern kernel. Formula more complex. Involves Bessel functions. Hyperparameters. Length scale controls the smoothness. Nu controls the smoothness of the function. Higher values lead to smoother functions. Key features. Offers different degrees of smoothness. Can be more computationally expensive than RBF. When to use when you need fine control over the smoothness of the function. 7. Dot product kernel. Formula kx1, x2 by 1 by 2. Hyperparameter none. Key features. Similar to linear kernel, but with the possibility of non-linearity. When to use for data with a clear geometric interpretation. Like image features. 8. Constant kernel. Formula kx1, x2 constant. Hyperparameter. Constant value sets the constant value. Key features. Represents a constant function. When to use to add a bias term or to model constant variations. 9. White kernel. Formula kx1. x2 noise level delta x1 x2. Hyperparameter. Noise level controls the amount of noise in the model. Key features. Adds noise to the model. Useful for regularizing the GP and preventing overfitting. When to use when the data is noisy or for regularization. Understanding the YAML keys. The provided YAML structure is not directly related to sklearn Gaussian process kernels but seems to be a generic configuration file. However, some keys can be mapped to common kernel parameters in sklearn. Here is an example of how you might define some of these parameters within sklearn's Gaussian process regressor. Python. From sklearn, Gaussian process import Gaussian process regressor. From sklearn, Gaussian process, kernels import RBF. Constant kernel. Assuming your YAML data is loaded into a dictionary called YAML data. Extract hyperparameters from the YAML. Length scale YAML data kernel length scale. Constant value YAML data kernel constant value. Noise level YAML data kernel noise level. Create a kernel using the extracted hyperparameters. Kernel constant value RBF length scale. White kernel noise level. Initialize the Gaussian process with the kernel. GPR Gaussian process regressor kernel. In this example, we define a kernel using the RBF and constant kernel. White kernel with hyperparameters extracted from the YAML data. The operator combines kernels, while the operator adds them. Important considerations. Hyperparameter optimization. Finding the optimal hyperparameter values is crucial for achieving the best performance. Techniques like grid search, Bayesian optimization, or gradient descent can be used. Kernel choice. The choice of kernel depends on the characteristics of the data and the desired smoothness of the function. Computational complexity. Some kernels, like RBF, can be computationally expensive, especially for large datasets. Data preprocessing, scaling and normalizing the data before training can significantly improve performance. Conclusion. Understanding the different kernels and hyperparameters available in sklearn's Gaussian process framework is essential for building accurate and effective models. By carefully choosing the kernel and tuning its parameters, you can optimize the model for your specific data and task.